Measurement of mechanical properties of composite samples with long fiber reinforcing. The determination of unknown parameters of composite materials has to be performed by experimental measurements. These parameters represent input data for numerical simulations. For a complete description of the properties, it is important to make measurements on both the fiber reinforcement, tau, and the matrix as well as on the resulting long fiber reinforced composite structures, matrix bonded fibers. Measurement of the mechanical properties of the samples is carried out according to standard laboratory tests, which are divided according to the time course of the applied load. Tests can be divided into static and dynamic. It can thus perform the tensile test at a constant or cyclic loading of the sample, 3-point bending strength, and Charpy impact test, as shown in Figure 3. The samples may be formed in the dog bone shape or, optionally, in the form of a rectangle of defined length L, width B, and thickness h, 3 whereas they can be used for short or long-term test. Determination of mechanical properties of composite samples, A. Tensile test, B. 3-point bending test, and C. Charpy impact test. The characteristic physical properties of samples of long fiber reinforced composites are influenced by weight and volume ratios of individual input components, fiber reinforcement and matrices, that ultimately affect design parameters, mechanical properties and weight of the structure. The mass and volume amounts of the fibers in the matrix in the composite structure sample can be defined according to the following relationships, 1 to 5. Where mc is the total weight of composite, mf, is the weight of fibers in matrix, mf, is the weight amount of fibers in matrix, vf, vm is the volume amount of fibers in matrix, vc is the total volume of composite, and vf, vm is the volume of fibers in matrix. Volume amount of fibers Vf and matrix Vm can be also expressed with the help of the fiber density ρf and matrix density ρm, which is applied in 6. The total density ρc equals mc/Vc can then be expressed as the sum of components, that is, the reinforcement and matrix, 7. The characteristic thickness of the composite structure can be expressed according to the relationship, 8. Gay and Hoa reported that winding of the fibers onto shaped geometry may achieve the volume fraction of fibers in the composite maximally 55 to 80% of the total volume of the composite structure. Ideally, these values can be increased by precisely placing fiber toes side by side. A limit state of volume fiber fraction, that is, 100%, cannot be achieved due to the necessity of the presence of the matrix. Also by perfectly precise laying of fiber strands, the strands will always have a certain fill value that will never be equal to 1 in the geometric configuration. Perfectly precise laying of fiber toes does not provide 100% of volume filling due to fiber cross-section. However, it should be noted that the optimum ratio of fiber reinforcement is in the range of the synergistic effect, that is, Vf 0.4 divided by 0.65. The influence of selected physical parameters on the geometric parameter h of some tested samples from long fiber reinforced composite structures is shown in Table 1. These parameters can then be used to establish numerical models. Other input parameters that are required for the numerical model have to be obtained by measuring the test samples. Other input parameters that are necessary for the numerical model are obtained by testing composite samples. Examples of physical and geometrical parameters of the selected samples of composite structures reinforced with long fibers. Note, mf*, represent area weight, mc*, is the total weight of composite,